In the everyday chaos, think about this unexpected question. What's the link between a small cup of hot coffee and the unseen force shaping the universe? An explanation for the unidirectional nature of time, also known as the arrow of time, is provided by this understanding. As you watch this video, entropy is all around you. Cells within your body are dying and degrading, the floor is getting dusty, the heat from your coffee is spreading out, weeds overtake gardens, and ancient ruins crumble. Zoom out a little, and businesses are failing, crimes and revolutions are occurring, and relationships are ending. Zoom out a lot further, and we see the entire universe marching towards a collapse. The inevitable trend is that things become less organized. The pole of entropy is relentless. Everything decays, disorder always wins. Before you get depressed, there is good news. You can fight back against the pull of entropy. You can solve a scattered puzzle. You can pull the weeds out of your garden. You can clean a messy room. You can organize individuals into a cohesive team. But because the universe naturally slides toward disorder, you have to expend energy to create stability, structure, and simplicity. Successful relationships require care and attention. Successful houses require cleaning and maintenance. Successful teams require communication and collaboration. Without effort, things will decay. Let's use a deck of cards to explain. When the cards are neatly ordered, it's like having low entropy. But when you shuffle them over and over, they become disorganized, showing high entropy. This change indicates the passage of time. No matter how much you shuffle, the cards won't magically go back to their original order. This basic idea applies to many things we see in the universe. However, it leads to questions when we look at organized things like stars, planets, and life. To understand this, think of entropy not just as a disorder, but as the number of ways you can arrange things without changing how they look or their energy. In our card example, each shuffle is a new arrangement, and entropy is all the possible shuffles. A commonly stated version of the second law of thermodynamics is the entropy of a closed system can only increase. However, this isn't an accurate representation of the second law. A more precise statement would be when a thermally isolated system transitions from one thermodynamic equilibrium, state A, to another B, the increase in its thermodynamic entropy S is greater than or equal to zero. It's important to note that entropy lacks a well-defined meaning outside of thermodynamic equilibrium, a subject still actively debated among researchers. However, in specific systems where we can continuously monitor a set of macroscopic variables over time, non-equilibrium entropy can be defined. There are certain concepts that are often overlooked. The one we're exploring here quietly shapes our universe. Influencing everything from particle interactions to celestial motions, this unassuming yet crucial idea might hold the answers to the mysteries of time and life. It steers systems towards increased randomness while preserving a delicate equilibrium, directing the constant fluctuation of both simple reactions and complex phenomena. Most of us here are already familiar with the notions of entropy and the second law of thermodynamics. In fact, in contrast to other quantities such as mass or energy, it seems that entropy is a subjective quantity that depends on the macroscopic variables that an observer chooses to define or has access to. All physical phenomena from atoms to galaxies are governed by this basic principle, yet the second law of thermodynamics seems to be a fundamental law driving our universe on the same level as the conservation of energy. During ideal processes, entropy remains constant, but in real-world processes, it increases. Thus, systems tend to become more entropy or more disorderly as they progress. In simple terms, when we talk about increased entropy, we mean that systems tend to move from less likely arrangements to more likely ones. Ideally, a system's energy should be evenly spread, reaching a balance with its surroundings. This leads to a puzzling question. Why doesn't the entire universe already have maximum entropy? To answer this, we look at the universe's initial conditions. It's assumed that during the Big Bang, the universe started with very low entropy. While the past hypothesis doesn't explain why there's so little entropy, it suggests that the universe had to begin this way for it to evolve. The connection between the arrow of time and the second law of thermodynamics helps explain why time moves only forward. The idea is that since our universe started with low entropy and systems tend to move towards higher entropy, all physical processes go from the past to the future. This perspective helps us understand why we see order in a universe that generally moves towards disorder. Living on Earth is crucial in this context. Earth isn't an isolated system. It receives concentrated low-entropy energy from the Sun. This energy reduces local entropy, allowing life to thrive. Life processes like growth and movement generate order, but they also follow the second law of thermodynamics by increasing overall entropy through the dispersal of energy. Far from contradicting entropy, life embodies it. In fact, life is seen as a direct result of this law, pushing the universe towards maximum entropy. This understanding makes entropy not just an indicator of time, but also of life's presence and development. Entropy was originally introduced by Rudolf Clausius in the early 1850s in order to describe energy loss in irreversible processes, which turned out to be very useful in predicting the spontaneous evolution of systems like chemical reactions and phase transitions. Back then, understanding entropy was a bit like grappling with a vague math concept. There wasn't a clear way to explain what entropy really meant. Then, in 1877, Boltzmann, who laid the foundation for statistical thermodynamics, came up with a neat way to define entropy. Simply put, he said that entropy is a measure of how many different tiny arrangements, microstates, a system can have while still matching the big picture conditions we observe, like temperature, pressure, and energy. In simpler terms, Boltzmann's entropy tells us about the hidden details of a system. When the number of possible microstates is higher, it means we have less knowledge about the true setup of the system. For instance, black holes in our universe have high entropy because we can only define their characteristics by their mass, charge, and spin. Since we only know these factors, there are many possible arrangements of matter inside the black hole that we can't pinpoint. So friends, what are your thoughts about this theory? Share them in the comments section. If you enjoyed this video journey, then like and share with Cosmic Explorers, and subscribe to my channel for more similar videos.